Hi, everyone. Welcome back to week 1, lecture 2. We're going to be talking about measurement. These topics are covering chapter 1 and the start of chapter 2 in the textbook. We will cover units, significant figures, dimensional analysis, and introduce vectors. In physics, we use International Standard or SI units. So time is measured in seconds, given by the symbol s, lowercase s. Length is measured in meters, lowercase m. Mass in kilograms, given by kg. And the rest we likely won't use this quarter. When we're working on physics problems, our units should specifically break down into seconds, meters, and or kilograms. This also means that we will need to convert units when they aren't in our typical physics units. For example, this value is given in miles. We don't use miles in physics, so we want to convert it. For this example, we are actually converting miles into kilometers. But depending on how we were going to use that distance, we may need to also convert from kilometers to meters. So to do the conversion, we multiply our value of 60 miles by a conversion factor. We figure out this conversion factor by first establishing how many kilometers are in 1 mile. So that's what this is, 1.609 kilometers in 1 mile. Then we structure our multiplication so that the units we don't want cancel out. So we have kilometers on the top and miles on the bottom. That way miles cancel out and leaves us with kilometers. This gives us our distance in kilometers of 97 kilometers. So now let's talk about precision and significant figures. When the length of something is listed as 3 meters, it's reasonable to assume that the true length falls somewhere between 2 and 4 meters. But if instead the length was given as 3.154 meters, we can assume that the true value falls between 3.153 and 3.155 meters. If we know the length is 3.154 meters, but we list it as 3 meters, we are withholding useful information. Now, significant figures. In determining how many significant figures are in a number, you start from the left and ignore leading zeros. So 3 meters has 1 significant figure, and so does 0.003 kilometers. We are ignoring the leading zeros in this, and the only significant figure is this 3 in both of these. If instead we have 3.0 meters and 0.0030 kilometers, they both have 2 significant figures. When we present numbers like this, we're saying that we are sure or relatively sure about the value of that trailing zero. So we don't just put a trailing zero to have 2 sig figs. So we need to feel confident in that value. An additional point about significant figures is that you should not include more sig figs in your final answer than what you input. For example, if we have 3.5, if we multiply 3.5 and 1.5, we get 5.25, but the input only had 2 sig figs. Each of these only had 2 sig figs, so our output should also only have 2 sig figs, and it should be 5.3 instead of 5.25. And this is true when there is a difference in significant figures between the two values you're multiplying by each other. So we have 3.5 that has two significant figures, and we're then multiplying it by 1.537, which has four significant figures. If we plug this into our calculator, we would get 5.3759, but the smallest number of sig figs we input was 2, so our resulting value should have no more than 2 sig figs. So we should round our value to 5.4 so that we're not assuming precision that we don't actually have. There's also the concept of the least significant digit or the first doubtful digit. So, for example, 5.3 implies a value between 5.25 and 5.35. And 5.33 implies a value between 5.325 and 5.335. Sorry, got distracted. When adding values, the final result should not be more precise than the least significant digit. So, for example, we have these three numbers added together, 2.5, 3.01, and 1.594. The least significant digit is the 0.5 and the 2.5. That only has two sig figs, and the least significant digit or the first doubtful digit of that is the 0.5. So that tells us that our result needs to stop at that same point, stop with those two sig figs. Because the least precise value is 2.5. We can't assume anything beyond that 0.5. So even though our other two numbers are more precise, when we're accurately presenting the information, we need to stop at the least significant digit. Another important concept is dimensional analysis. In this example, we talk about force, which we'll learn about later in the quarter. But force has units of newtons, which are kilogram meters per second squared. So let's break that down. Kilograms, units of mass. Meters are units of length. Seconds are units of time. So force is mass, length, and time to the -2, or divided by time squared. Let's do a quick self-check here. Feel free to pause the video and answer this question. I'll read it first and give you a second if you decide to pause. So velocity is in units of meters divided by seconds. Which of these shows velocity? Is it A, L times T? Is it B, M times T? Is it C, L times T to the -1? Or is it D, M times T to the -1? I'll give you a second here. Okay, the answer is C. It's L times T to the -1, or length divided by time. Okay? Now, vectors. We're going to be using vectors a lot because a lot of quantities in physics have both a magnitude and a direction, which is described by a vector. So the length of the vector, so here, shows the magnitude of the quantity, and the direction of the vector tells you the direction of the quantity. This is how we're going to work to understand vectors. Here is a diagram. We have a vector A at an angle phi from the positive x-axis here. We can break this vector into its x and y components using trig. The x component is adjacent to this angle, so that's going to be cosine. So that's what this term is. A sub x equals a times cosine of, oh, I'm sorry, that should be phi. It's listed as theta, but it should be phi for this example. Then the y component is opposite of the angle, so it's listed on the y-axis here, but you can also think of it here if you want to make the triangle, and that would make it opposite of the angle, so that would be sine. So a sub y, or the y component of the a vector, is a times sine of phi. Remember, that's phi. So if we only know the x and y components, we can find the total vector using Pythagorean theorem. The square, that's this here, the square root of the x component squared plus the y component squared gives us the total vector. We can also find the angle if we only have the components and we don't know the angle using tangent. And finally, here is how, or a way to represent a vector. So vector A is the x component of vector A times this I hat, is what this is called, plus the y component of vector A times j hat. Let's take a quick look at this I and j hat really quick. So I and j hat are unit vectors, unit meaning one. So they don't alter the magnitude of the value, they just tell you if they're in the x or y direction. So these just both have a value of 1, and then they get multiplied by our x and y components to show us that this is the x component, this is the y component. Because we're not always going to label them a sub y, a sub x. Sometimes they'll just be numbers. Let's talk vector addition. So first, look at figure A here. It shows two vectors, vector A and vector B. We want to know what vector S is, where S is the sum of A and B. To do this, we move vector B so that its tail starts at the tip of vector A. So that's what we do without changing the magnitude or angle. And then we draw a vector from the tail of A to the tip of B, and that is the S vector, or the sum of the two. It's another useful graphic for this. So just walking you through the steps explicitly, you have two vectors A and B, and you want to know what the sum of them is. You draw vector A, then you put the tail of vector B at the tip of vector A. So remember, tail is the bottom, tip is the end. And then finally, you draw an arrow from the tail of the first vector to the tip of the second vector, and that is the sum of the two vectors. We can also do this sort of vector addition if we numerically, using the I hat, j hat representation of the vectors. So if A is given by these x and y components, and B is given by its x and y components, then the sum of the two vectors is just the sum of their x and y components. So the x component of S is just the x component of A plus the x component of B times I hat. And the y component of S is just the y component of A plus the y component of B times j hat. And you can see this same method visually instead of just numerically, because we are showing, so like here's the x component of A and the y component of A, and then the x component of B and the y component of B. And you see how they combine to make the x and y components of S. So we'll start with y here. Both the A and B y vectors are positive, like in the positive y direction. So they just combine to give us S, the y component of S. But then for the x component of them, the x component of the A vector is positive, but the B component, or the x component of the B vector, is negative. So it needs to subtract from the A vector, giving us a smaller x component of the S vector. Vector subtraction works just like vector addition, but we take the negative of the subtracted vector. So let's say A minus B is D. To find that, we do vector addition of A and negative B. So we draw vector A, right? And then we draw negative B vector starting with its tail at the tip of the A vector. So that's what this is. It's just B in the opposite direction because that's what the negative does. And then again, the same thing here where we go draw a vector from the tail of A to the tip of negative B. And that is vector subtraction. So it's really just vector addition of negative of the vector. And so a vector has a magnitude and a direction. Like I said, magnitude given by the size of the vector, direction given by the direction of the vector. A scalar just has magnitude. So if you multiply a vector by a scalar, it only changes the magnitude, not the directions. That's what's happening here. Our vector is A, and this vector here is 1.4 times A, so the scalar is 1.4. And this vector here is negative 0.5 times A. So again, the scalar is negative 0.5. But you can see with all of these, the angle that the vector is at is unchanged. And the direction for this one does change when you multiply it by a negative. Next up, you need to complete your post-lecture self-check. Submit your discussion post and reply to someone else's. Work on the application assignment, it's not too long. And watch the last lecture for the week.